So with so much information, I wanted to do a quick summary for you. You'll find this on the kind of the middle of the third page of your notes. So if you are given a function and asked to find the derivative or the slope of the tangent line, then you'll need to use the definition with delta x in it. So the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. This will give you a formula. I think that's the thing that you need to know. This will give you a formula. So it'll have something like 3x or 2x squared or something like that for you to find the slope in terms of x. And then if you're given an ordered pair, you could substitute in the x value of that ordered pair in order to actually find a numerical value. But a more straightforward approach would be if you're actually given an x value, so you're given a number, then you can avoid using the delta x, and you can use this version of the derivative definition, where the limit as x approaches c of f of x minus f of c over x minus c would be used. This will give you a numerical value of the slope at x equals c. So the advantage of this one is that you go right to the number value. The advantage of this one is that you're given a universal formula that you could use and then use any x value that would be on your original function. So there's a summary of the two definitions of a derivative and when you might want to use either one. The most universal would be this one. It could be used even if you're given a numerical value because you could just substitute that at the end. So this would be the most universal one to use. So then down at the bottom of this page, you will have a few problems where you're asked to determine whether a function is differentiable. So to determine differentiability, the first thing to check would be continuity. So I asked you on these examples to describe the x values at which f is differentiable. So for this one, I can see that I have a rational function and my denominator, x plus 1, could be a problem, and it is. Because if I set x plus 1 equal to 0, I get x equals negative 1. So f is not continuous at x equals negative 1, and therefore not differentiable at x equals negative 1. And since I asked you for where it is differentiable, you could say it's differentiable on negative infinity to negative 1 union with negative 1 to infinity. But make sure that you're not using a bracket because it is not differentiable because it is not continuous at negative 1. If you have a piecewise graph, as we did in the previous chapter looking at limits, we would need to make sure that the limit, so for this problem, for the graph to be continuous, the limit as x approaches 1 from the left, in which case I would use x to the third minus 3x to the second plus 3x, has to equal the limit as x approaches 1 from the right. And in that case, I would use x to the second minus 2x. So we would have to check those two limits. If I plug in 1, I get 1 to the third minus 3 times 1 squared plus 3 times 1. This side's going to give me 1 minus 3 plus 3, and I'm going to get a 1. On this other side, we'll look to see if they're equal. So I plug in 1 from the right, and so that would be 1 squared minus 2 times 1. And so I get 1 minus 2, and that's -1, and they are not equal. So this limit as x approaches 1 of f of x does not exist, which would mean that f is not continuous. And therefore, and not differentiable at, excuse me here, at x equals 1. And so once again, you could describe where it is differentiable, since that's what I asked you. So it would be differentiable on, and then give your intervals -infinity to 1, union with 1 to infinity. So that would be one thing to investigate if you're asked to determine whether a function is differentiable, is to check its continuity. If you have a polynomial, if you have a sine or a cosine function, those are going to be continuous on the whole number line, on the real number line. And so those will be differentiable on -infinity to infinity. But if you have these kind of red flag functions, then you know that you need to look at where these functions are continuous. And so there are a couple of examples tying that together. Now, the other part that you have to check is if you do have a continuous function, then you've got to make sure that the limit definition exists for every point in that interval. And one of your red flag functions should be absolute values. So I have a part B. I'm going to have to erase and do that part B for you. So again, we're still asking the question about differentiability. And this time you're in the section where you're going to check for the existence of a limit. And so therefore, in our example, where it asks, is this function differentiable? So is f of x, which equals the absolute value of x plus 3, is that differentiable at x equals -3? So I'm actually asking you for a determination at a certain x value. So is it differentiable, this function, at x equals -3? Well, what you'll need to do, because it is continuous, an absolute value function is continuous, but let's look at the limit as x approaches -3. Now, I'm going to be using that definition of a derivative for when I have a specific value. So that would be the second one that I gave you, and that was f of x, so x plus 3 in absolute value, minus f of c. That means I'm going to be plugging -3 into the x over x minus my c value, which was -3. So I have to check that and find out if f prime of -3, that's really what I'm looking for here, if that limit exists. And if it does, then I know that it's differentiable at -3. And if it does not, then I know that it is not differentiable at -3. Well, so if I check this, I have the limit as x approaches -3 of the absolute value of x plus 3. This gives me -0 over x plus 3. Now, that also should look familiar to you. I had you investigate this or something similar to this on your last test. And so if you plug in -3 here, you get 0 over 0, indeterminate. And so this, you have to remove the absolute value and look at the limit from the left and from the right. So that's what we'll do here. I'll remove the absolute value. I'll have us do x approaching -3 from the left. As we do that, removing the absolute value, you use the left branch. And that would be the negative of the quantity x plus 3 over x plus 3. Those will cancel, and you'll end up getting -1 for that limit. And then I'll have to make sure, does that equal? So this is what I'm trying to figure out. Does that equal the limit as x approaches -3 from the right? Well, from the right, removing the absolute value, I've used the positive branch. So x plus 3 over x plus 3. I can cancel, and I get a 1. And obviously, -1 does not equal +1. So I can go back up here and say that that limit, as x approaches -3 of the absolute value of x plus 3 over x plus 3, does not exist. And because that does not exist, then I know that f is not differentiable. F is not differentiable at x equals -3. And that's what this question was. Wanted to know, is the function differentiable? And if you will think about it, at -3, that is where this function would have a sharp turn. It's an absolute value function, and the vertex happens at -3, 0. And so at the sharp turn, at the vertex, this function's the definition of the derivative failed to exist, and so it is not differentiable at that sharp turn where the vertex occurred. So this is the end of your introduction to derivatives. So you'll be working when we return to homework 11, and I hope that this will be able to help you as you begin this